In today's notes, we're going to learn how to balance redox reactions. What's special about balancing redox reactions is that you need to balance the charge. We've talked about how all chemical reactions must conserve mass, energy, and charge. So now we're going to show you how that charge is conserved when we balance these redox reactions. There's really only one step in this process that is something you've never done before, and it's not hard. The hard part about this is, of course, using the skills we've already learned. The first thing we're going to do, and I'm going to write this up in the steps, is assign oxidation numbers. Hopefully you've been getting some practice in assigning oxidation numbers so that this is something you're good at. If you haven't, make sure you practice some more. All right, first thing I notice when I look down at my redox reaction is that the first compound has a polyatomic ion in it. So I should probably look up in table E to find out what the oxidation numbers of N and O3 together make. When I do, I find it's -1. And that's not something you necessarily have to do, but nitrogen, when you look it up in the periodic table, has a lot of oxidation numbers. So being able to look at just those two elements may make it a little easier on you. So oxygen is always -2. And since there's 3 of them, that's a total of -6. Now the NO3 has to total -1, which makes nitrogen +5. And then the -1 on the NO3 is balanced off by a +1 on hydrogen. Sulfur, just like any element when it's by itself, is 0, unless you're told otherwise. And now on the product side, we're going to again see nitrogen. So let's fill in oxygen first. There's 2 of those, so that's -4. The whole thing has to total 0 this time, so N must be +4. Well, we have another polyatomic. SO4 totals -2. You can get that from table E. Oxygen is -2 times 4 is -8. If that's going to total -2, that means sulfur must be +6. And then there's 2 hydrogens to balance off that -2 from the sulfate, but each one by itself is +1. And then water again, oxygen's -2, hydrogen's +1. The next thing we're going to do is we're going to look at those oxidation numbers to determine which elements gained and which element lost. Again, not something new. You've had to do that in order to write half reactions anyway. So looking at our elements, it seems that hydrogen was +1 and +1 and +1. It's not hydrogen. Nitrogen here is +5, but here it's +4. So that actually went from +5 to +4. Oxygen here is -2, -2, -2, -2. So it's not oxygen. And then sulfur is 0 and +6. So there's our other one that changed, was sulfur. So we have nitrogen going from +5 to +4, and then sulfur going from 0 to +6. So the next thing we're going to do is we're going to write our half reactions. Again, not something new. I'm going to abbreviate reactions RXN. So now we're going to have to identify which one was oxidation and which one was reduction. I have a hard time identifying oxidation, but I don't have any trouble, for whatever reason, identifying reduction, so I'm going to do that one first. Reduction means that the oxidation number was reduced. The oxidation number went down, and that happened with nitrogen. It went from +5 to +4. So we're going to write our half reaction for reduction based on nitrogen. Nitrogen started out at +5 on the reactant side. On the product side, it was +4. When we put in our electrons, we always put the electrons in on this side with a higher oxidation number, since they're going to pull down the charge being negative. In the end, you need to have the same charge on the reactant side as you do on the product side. So I'm going to need 1 electron on the reactant side. So that means that sulfur was oxidized. Sulfur went from 0 on the reactant side to +6 on the product side. Again, we're going to put the electrons on the side with a higher oxidation number, and the charges need to be the same. So sulfur is actually going to lose 6 electrons, like so. Now here's where things get a little different. What we have happening here is sulfur is losing 6 electrons, but nitrogen only picked up 1. What happened to the other 5 electrons? That can't happen. So we have to make sure that this balances out by making sure you have the same number of electrons lost as you have gained. To do that, we're going to put in coefficients, just like we did when we were just balancing normal reactions. So I'm going to put a 6 out front of this reaction, and when that distributes through, I need a 6 on my N+5 compound, which was this compound here. So I'm going to put a 6 here, and then I'm going to need, this will make this 6 electrons, and I'm also going to need a 6 in front of my N+4 compound, which was this compound here. At this point, we have balanced the charges. That doesn't mean, however, that all of the other elements are balanced. So we now just need to balance everything. So we're going to balance just like we normally do, and we're going to count up all our elements. I'm not sure I left myself enough room to do this, but I'm going to try. Now typically you won't need to change the coefficients that you've put in as your coefficients from balancing your half reactions. So those you can pretty much leave alone. So let's count up what we have. With this coefficient of 6, I have 6 hydrogens, 6 nitrogens, and I have 6 times 3 oxygens, which is 18, and I have 1 sulfur. On the product side, I have 6 nitrogens. I'm going to hold off on the oxygens for a minute because they're in 3 places. Hydrogen is in 2 places here, and it's 2 and 2 for 4. Sulfur is 1. Now to count up all of our oxygens. For this first one, we have 6 times 2, that's 12, plus 4 is 16, plus 1 is 17. So right now the only thing that's off is our hydrogen and our oxygen. And lucky for us, those are both in the same compound in water at the end of the equation. So if I double that, now I have 2 hydrogens from sulfuric acid and then 4 from the water, that's 6. And then my oxygens, again 6 times 2 is 12, plus 4 is 16, and then this 2 makes this 2, so that's 18. And we are balanced. And then just to be sure, just to be safe, I would go ahead and fill in 1s in case they ask you for the sum of the coefficients. All right, let's do another example. Our first step is to assign all of our oxidation numbers. It is helpful to have table E when you have polyatomic ions. I'm nerdy enough, I have those memorized. Also, having the periodic table is helpful in looking up oxidation numbers. But again, I'm nerdy enough, I have them memorized. That Cl2 is 0 because even though it's 2 atoms of chlorine, they're bonded to each other. All right, now to identify our oxidation and reduction half reaction, we have manganese at +7 here and +2 there. So it was reduced. Mn +7 became Mn +2. So it must have gained 5 electrons. And then chlorine, interestingly enough, you see a -1 here, -1 here, -1 here, but a 0 here. This is going to get really tricky because we have chlorine in so many different places in our reaction. This is going to be probably the most difficult one you're going to ever see. So we have chlorine -1 becoming, and I'm going to bring my subscript over, and you'll see why shortly, which means that it must have lost, now here's where things get tricky, it lost 1 electron, but we actually have 2 chlorines here. So that means I actually need a 2 here in order to lose the 2 electrons that chlorine lost. Okay? It's going to get worse before it gets better, to be honest with you. Now, our next step is to make sure we have the same number of electrons in each. So we're going to multiply this one by 2 and this one by 5. When I multiply that, I get 10. So I'm actually going to have a 10 here. That number is going to change. And then I'm going to put a 5 here. And then this gets a 2. And then this one's going to get a 2. Okay? Normally, you wouldn't need to change the coefficients again. But because of the issue with chlorine being in so many different places, we are going to need to change that coefficient. Again, this is way harder, hopefully, than you'll ever see, but I want to be sure you're prepared. So I'm going to list my elements, K, Mn, O, H, Cl. Wish I'd left myself a little more room. All right, now we're going to count those up using the coefficients I already have in place. I have 2 K's on this side, and on the product side I have just 1 in the KCl. And then Mn on the reactant side, when I distribute that 2 through, I have 2 Mn's. And on the product side, I also have 2 with the coefficient on the MnCl2. Oxygen on the reactant side, again, I have to distribute that 2, so that's 8. And on the product side, I only have oxygen in one spot this time here in water, and with no coefficient there, I only have 1. So we know that's something that's got to change. Now, for hydrogen on the reactant side, with this coefficient, that makes it 10 H's. And on the product side, again, I only have this one spot where I have hydrogen, and with no coefficient currently, there's just 2. And then chlorine, on the reactant side, it's only in one spot, and with the coefficient, I have 10, which is a good start. But on the product side, I have 1 here, 2 times 2, which is 4 here, so that's a total of 5. And then 5 times 2 here, which is 10, so that makes a total of 15 CLs. Now, you've balanced with me before, so you know that the most complicated things I save for last, because most of the time those things are going to balance themselves out when you balance everything else. So instead of starting with CL, I'm going to start with K. So looking at our issue with K, we have 2 on the reactant side, but only 1 on the products. So I'm going to go ahead and fix that by putting a 2 here. And now I have 2 Ks. I've also changed my CLs. I have 1 additional now, so I have 16. It's a good idea to recount those to make sure you counted them right the first time, so I'm going to go ahead and do that with you. We have 2 CLs here, so that's 2. 2 times 2, which is 4, plus the 2 is 6, and then 5 times 2 is 10 for a total of that 16. So we did count that right. Most of the time, if you can't get something to balance, is because you've counted something wrong. All right, next thing that's off are oxygens. We need 8 oxygens on the product side. So I'm going to go ahead, change this to 8, and now I have my 8 oxygens. However, at the same time, I have messed up my hydrogens. My hydrogens on the reactant side are 10, but now my product side, they're actually 8 times 2, which is 16. Not exactly the number I was hoping for. But what I see happened, and another good lesson in why you do this and wait till the end for your hard ones, these are both 10, these are both 16, and they are both in this compound here. So we can actually change this coefficient to 16. That fixes this, and it's balanced. And that's how you balance redox reactions. I've shown you an easier one, and now a really difficult one. The only other thing they could ask you to do, besides the 2 types of examples I've shown you, is sometimes they only give you the half reactions, which is actually pretty super. So they give you the half reactions, like these, and ask you to balance it. Or they'll give you only the elements that are changing and leave out the spectator ions, which also makes it easier because you don't have to do this last step. So make sure you try the practice questions, and hopefully you will master this.